Welcome and thanks for watching the first law of thermodynamics, problems in solid phase. This is part 2 where I like to show you the isothermal work is completely ignored and not counted in the internal energy. So let me go back to the basics and start with the expression of the first law, which is expressed as the differential of internal energy is equivalent with dQ plus dW, where Q is the heat and W is the work. If we accept these are interchangeable, and I was pointing in the first part is maybe not the case, then we can sum it and adds up to the internal energy. This basic relationship it can be expressed in many different ways, and it's usually done by what of the variable is conveniently measurable. One of the most popular expressions and way to calculate the internal energy of a system when the heat is counted at constant volume and the work is counted at constant pressure. Thus, dU is counted as dQ by the volume is constant plus dW by the pressure kept constant. So in this way we can write the internal energy of N times dV times dt plus minus P minus P thermal times dV. Number of moles, molar heat capacity at constant volume, change in the temperature, pressure, thermal pressure, and the change in the volume. Well, we're supposed to sum all the energy in the internal energy. And if you look at these expressions, you can see that there is no term for the thermal work, isothermal work. Isothermal work can be done at constant temperature, and I can do work which is done at constant temperature. And this work should be counted in the internal energy. However, there is no terms for this kind of work. And the reason behind it, of the neglection, most likely it's a false belief, which is at constant volume, no work is done. This is far from the truth, and it's completely wrong. So let's see why. The pressure-volume relationship in solid phase, this would be the volume, this would be the pressure, and the volume can be schematically shown like this. Initial volume, temperature is constant, and as I'm increasing the pressure, the volume is increasing. So let's see a point here where the pressure is P1 and the volume is V1. How much work is done on the system? You have to integrate and you will get exactly the area of this triangle is equivalent with the total isothermal work. Okay, let's see. The temperature is changing. So the same relationship, and the relationship is not linear but exponential, but for our purpose this doesn't make any difference. So go back again, that's the volume, that's the pressure, and let's say this is temperature 1, and I'm at this stage, pressure 1 and V1. So the isothermal work and under these pressure, volume, and temperature conditions is equivalent with the area of this triangle. So this is the isothermal work in situation 1, which is T1. If I'm increasing the temperature, then the pressure-volume relationship changes, and at higher temperature, this relationship will be higher. So that means T2 and T2 is bigger than T1. So let's see what happens if I'm increasing the temperature at constant volume to T2. So by increasing the temperature at constant volume to T2, I'm moving along this line because I'm keeping the volume constant. Volume 1 is equivalent to volume 2. However, the pressure is increased. And the pressure now is P2 at constant volume. So what is the work, the isothermal work at this point? Is the integrated area of the triangle of this. So no question, WP2 is bigger than WP1, thus isothermal work on the system is done at constant volume, and this is not counted in the internal energy. Thank you, and hope you will see part 3. Bye.